I've revised my answer by setting an expression for power equal to 0 and taking the derivative of that expression with respect to ZL. It is possible to find the maximum, the inductance that maximizes the power delivered to the speaker. And here I have an expression with just V source and ZL, which when I take the derivative with respect to Z and set it equal to 0, I get a nice clean radical 50 ohms for that inductance. That would give you the maximum power. For assignment number 7, question number 1, I had an error in these outputs. The sum of these numbers is 1, which means that this simply can't be true. It would have to be C is 0 and S is equal to 1. Here I have the S function, and it is true that S is equal to 1, X and Y not, and X naught and Y naught not give you an S of 1. For number 3 on assignment number 8, it is not true that you only need 2 logical functions, so you would need 3. The maximum sum in decimal is 6 when adding two 2-bit binary numbers, and you would need 3 logical functions to express this in binary. For assignment number 8, question number 4, I have revised the truth table to reveal that 0, 0 and 1, 1 inputs are both unstable conditions, because as the flip-flop gate takes those two conditions, they only are different for a very slight time period in between and still remain to be the same, and does not satisfy the goals of a flip-flop, the purpose of the flip-flop gate. So those two states are unstable. In assignment number 5, question number 2, you can see here that I've converted this little 4-bit decimal number into hexadecimal by dividing 3 by 16, which is the base of hexadecimal. You can see that I've found the hexadecimal values of these numbers. When I break this down into binary, I first convert the hexadecimal into decimal, just standard base 10, and I take this into binary and split each number into binary so that I could see which numbers are 1s and which numbers are 0s, and here you get 2 to the 7th plus 2 to the 4th plus 2 to the 0, and all that matters is these first two numbers being 1 and 0, which shows this is a class B network. For question number 3, I've simplified this function to x and y, or x prime here. You can see in my first step I have x prime and y, or x prime and y prime. There's no reason to use both of those expressions when you know that no matter what is paired with x naught, it will be positive. For question number 4, I proved De Morgan's theorem by comparing these two equivalent pieces of the De Morgan's theorem and showing that their outputs are identical. In both these cases, this is true. That's number 4 again.